Last portion that is a little bit more, I don't want to say boring topic, but this is what is called the more relevant to the actually, this is the third law. Okay, the title is third law, and this is actually third law topic, which is a sort of the added on to the second law. And what's the can we actually measure my S? And we actually just talked about the caloric way. And we can, as a human being, that we can easily measure what we can measure. We can measure volume pressure and temperature, right? And also we can measure how much heat we generate, and those are the ones that we can do. So you already we talked about this. So therefore, certainly delta H can be measured in a normal, like a constant pressure situation. Temperature can be measured, and also you guys can measure the heat capacity, number of moles. So this is something that all related, and we can measure that. So this is what we have covered, and when there is a phase transitions or some kind of temperature change or the volume change. And we are mainly actually more concerned about the temperature effect. And the most important one that here is what do you mean by third law? I'm pretty sure we're gonna quickly forget about it. Is entropy is 0. Okay. That will be cool, right? If you know entropy is 0, and that's for perfect crystalline solid. Okay? So from our experience, matter can exist as a gas and liquid and solid. Solid is much more ordered, organized structure, so they should have the lowest entropy. And we make it crystalline, and we make it there's no defects, right? And at temperature is 0 Kelvin. That's a statement. Okay. So wow, that's very nice. I'll just put a little comparison. Okay. So do you remember the delta H formation for in the standard state is 0 for what? Do you remember? Pure elements, right? You remember that? Delta H formation of hydrogen gas, that will be 0. We kind of happily know that, and that's has been very useful for us to calculate heat of reaction. This one is not attainable. This one is attainable. This has a reference point. And you will actually also learn about the formation of Gibbs free energy will be 0 for pure elements. So this is something that is coming later on too. Okay? I just want to give a heads up on that. But delta H and delta G is something that we can easily deal. But this statement is, I would say, is a philosophical statement. The problem is, yes, can you make perfect crystalline solid? Yes, we can. Okay, yes, we can. But can you get to there? Okay, and the answer is no. Okay, so that's far. Nobody has succeeded so far. And if you ever succeeded, you will get a Nobel Prize. If you want to do that. So the one way is, this is a one way to say second law, and another way to make a second law statement is. Number 2 is temperature 0 is not obtainable. Or I would say S is 0 is not obtainable for finite number of pulses. So that's a statement that second law of thermodynamics. And you know, when we talk about the perfect crystalline solid, we are not only talking about atoms, but the, you know, some of the atom has a magnetic spin. They all has to be paired up perfectly. If you have this one coming down, it's not going to be the lowest entropy state. So this is actually fine print that, yeah, we can locate all the things in a regular lattice and so on, but also if there's an electron spin, they have to all paired up and has to make a perfect one. This is not easy to be attained, or is impossible to attain as far as our human experience is concerned. So this is a third law state. But you know, because of the statement that I just made, I can draw this. So most people would like to change the matter, and we observe this. The matter is changing from solid, liquid, and the gas, right? Increasing the temperature, we are seeing this. Sometimes with the liquid is bypassing, we just observe the solid to a gas transition, that's a sublimation. Okay? The other way does not happen. Okay? If you heat it up, gas becomes solid, it's not going to happen. That one I can prove that, and this is part of the purpose of this class. We typically see this, you have an ice, you have a liquid water, and essentially water vapor is coming out, and that's it. And then I will just graphically, conceptually understand what this S means. And although it's not attainable, let's say the 0 Kelvin is right there. And so your entropy is supposed to be 0 here. Okay? And so that's your starting point. And then it's going to go up. That's the sort of a diagram that you can see how entropy at different temperature, as you increase from 0 Kelvin, entropy is going to go up because things became more disordered. And then this one is represented by, I can't call it, this is a melting temperature, if I call it. And this one is boiling temperature. Right? Somebody say, well, that's a fusion temperature. Somebody called that's a vaporization temperature. It's up to anyone who wants to put a different symbol there. But anyway, this is a solid, this is a liquid, this is a gas. Okay? And this continuous change is always happening, and that is, I guess, delta melting of entropy divided by melting temperature, and this continuous increase is delta H vaporization, entropy change, so you can think about that. And then this portion is always can be derived by Cp Tf. Right? But there is actually, if you remember that, I need to step back. Okay, so really, okay. So what was original was Cp dT, right? That's your heat divided by temperature, and you want to change from, I guess, the initial temperature to the final temperature. To drive this equation, I already assume that's a constant, not temperature dependent. For liquid and the solid, this is quite temperature dependent. Okay? In the textbook and your exercise problem, say, well, Cp is an A times Bt plus, I think a C over T over square or something. They give out this empirical formula. You don't forget about it. You need to crack the ball. This can be a temperature dependent term. And then you need to put it in and do this ugly math to calculate those. Okay? So that's a reality that this one does not have to be constant. Not necessarily. This is actually temperature dependent. And you can imagine that the higher you go, the molecules will move faster, so they have a different energy to raise up the temperature, given the same amount of heat is being provided. So that's really the scenario. But what I think is important here is, yeah, I know that, and this is probably strictly speaking, they are temperature dependent, right? They always do that. But also remember that if you are interested in temperature change in this region, right? And my temperature region is here to there is this much. Although this is there, the CP is temperature dependent, I can see that this is CPM is sort of constant. I can approximate that. Right? If you do that, I can use this equation. This equation is always pops up many, many times. They give you, this is a CP, is strictly speaking, they are, and CP is CP is constant. Yeah, this equation is true, but at the same time, CP can be approximated to be constant when your temperature window is narrow. Right? That's also the conceptual thing that sometimes you just have to you just have to do it in a more like an approximate way. Okay, so that we cannot really do all the things. Sometimes you can spend 2 hours to get the exact answer, or you can spend 5 minutes to get the right approximate answer. Which one is what would you do? I would do 5-minute approximate answer. That will give you quite kind of give you a nice idea about what the answer should be. Right? So remember that this equation is always true, and strictly speaking, this is a temperature dependent, particularly for those. They are true. For the gases, it's kind of okay to be a constant value. You remember the CP is like that. The CPM is CDM plus R, ideal gas, and this is typically 3/2R for a monoatomic gas. So this is a sort of a constant value. But as far as the liquid and the solid is concerned, this is not a constant value. At the same time, like I said, you look for the temperature ranges. If this is a sort of not so big, let's say 10-degree differences, 20-degree differences, you just calculate those two values and get the middle value, and that's my numbers, and you can just using that equation. Probably that was not a bad idea to kind of go around the problem. Okay. One last one that I need to say. It's also practice. It's not well done, but I need to write it this. This is quite similar to what I have held before. So in number 2, delta S, standard state for the reaction. Okay? So this case, so this is a standard reaction entropy change. Okay? So this is what I need to know. And this equation looks very similar to what we've been dealing with. This one, product mu times S P for molar. So this is a per mole basis. So that's this, and then this is number of moles defined by your reaction. Reactant. So that's the equation. So this is missing. That's the equation that we use. And you can see that there is equation that there is an example in my class note. I'll just give you a little from that. So let's just give an example, and then you will see what this means here. So I have a H2 gas, oxygen gas, H2O, and the temperature is 298 Kelvin. And you're going to looking at what's my entropy change for this. And then I will do, okay, so molar entropy, this is a 1, right? So this is a 1. And for water, you just wait, you do the bookkeeping, that's a product. And the reactant, which is a minus this, which is a SN H2 gas minus half of SN O2 gas. So that's an equation that I can write. And these are the values, okay? The standard entropy that was defined from absolute zero entropy, that's in the table 2C4 of the textbook. If you look at the thick textbook, at the end there is a 1 and you can read those numbers. And you can plug it in and you can calculate those. And what I'm saying here is, don't be deceived by this. This is a pure element in the standard state, right? Of 1 bar pressure, they are gas, right? But this is not zero. Okay? All because of the entropy, this is non-zero. This is non-zero value, right? So remember that. It's only true non-zero or true zero entropy is defined when you are in the solid state. Perfectly crystalline solid. This is not a solid state perfect crystalline solid. So this does have numbers.